Dear participants of this course on micro irrigation engineering, now I am inviting to lecture 27. Lecture 27 is dealt with tutorial class 5. This tutorial class is on design of drip irrigation system. We have given theoretical aspect of design of drip irrigation system. So, here numerical problem and then how a drip irrigation system design can be made by given set of data. So, a question is given here for the design of drip irrigation system, which is to be done for a citrus crop of 1 hectare orchard area with the length and breadth of 100 meter each. This crop has been planted at a spacing of 5 meter by 5.5 meter, and pan evaporimeter data will be used to estimate the water requirement of the crop. So, pan data is given, this is during summer month, means this is during peak demand period. So, value is given as 8 millimeter per day. There are other relevant data to this problem. The system is to be laid on a sloping land, and then slope has been provided in the upward direction from south to north direction. The water source is located at a southwest corner of the field, and it is a well. Soil is a sandy loam in texture, and content of different proportions of clay, silt and sand, these are also given. Field capacity is 14.9%, wilting point is 8%. The bulk density of the soil is 1.44 gram per cubic centimeter. Effective root zone depth is 120 centimeter, and from crop point of view, the area to be weighted by drip emitter is 40%, that is a percentage weighted area. The pan coefficient is 0.7, crop coefficient 0.8, and then static water level, static water head, that is 10 meter, and pump discharge is 2.5 liter per second. So, these are the data which are relevant to this particular field. Maybe some data we will need at the time of design. So, we need to assume which will be relevant to the this particular situation. So, when we come to the solution, the first most point to be considered is estimation of water requirement of the crop. So, we will be estimating the ETC of the crop, and this ETC is nothing but the evapotranspiration requirement of citrus crop, which can be estimated from the pan data. So, we have been given the value of evaporation from the open pan, that is 8 millimeter, pan coefficient is 0.7 and then Kraft coefficient is 0.8, and if we multiply all these parameters, then one can get ETC in millimeter per day. This ETC in millimeter per day can be converted to a liter per day if we multiply with the area of each individual plant, but in drip irrigation system we are not weighting the entire area. So, area that we will multiply with the percent weighted area. So, area covered by each plant is 5 meter by into 5.5 meter, and percentage weighted area is also given to us, that is 40% or 0.4, and then the evapotranspiration requirement of the crop, which we have calculated as 4.48 millimeter per day. So, this is equivalent to, when we are multiplying, this is this can be, this we will get in cubic meter per day. So, this cubic meter per day is converted in the form of liter per day. So, which is coming as 49.28 liter per day or 50 liter per day. So, this way we will get, for each plant we need to supply water of 50 liter per day. Now, this 50 liter per day is to be given water with the help of a drip emitter. So, it comes for the selection of appropriate size of the drip emitter, and this will be selected based on considering the soil texture. So, soil is sandy loam, crop root zone system, means up to what depth the water is going. So, this information is also given. This is a crop which is a deep rooted crop 1.2 meter, and then so considering if we are giving a dripper of 4 liter per hour, and since water requirement is large, this is 50 liter per day. So, the one dripper will not be enough, but we have to provide sufficient number of drippers, and then and this water is to be given in this flow rate, that is, this is the characteristic, so that the weighting can be made. So, we have selected 3 drippers which are placed in a triangular system or triangular pattern, so that the effective root zone area of the crop can be weighted. So, 3 drippers of 4 liter per hour will deliver in 1 hour 12 liter of water. So, this 12 liter of water, when it is supplied, it will require 4 hours 10 minutes to give 50 liter of water. So, means one plant or all the number of plants, each plants will which is coming in 1 hectare area, we have to operate the drip system for 4 hours 10 minutes. This is one of the important information which we have generated when we are considering a dripper, 3 drippers of 4 liter per hour. Now, in the question it is given, the well is located at the southwest corner of the field. So, this is the thing that somewhere the field is, means well is located at the southwest corner. So, this is a pump house, and then water is pumped by using a pump, and then we are connecting with the help of pump the drip system. So, from the pump water is taken to the filter, and then here there will be all control head assembly will be installed, means a filter, a fertigation unit, all that it will be installed there, and from there we are connecting a main pipeline. So, main from the it is coming a main pipeline, and we are bringing this main pipeline is 50 meter. Now, here this is one of the layout. It can be made in otherwise also. It could have been taken from the your main goes here, and then you are connecting main up to bringing it up to this place, and then sub main can be brought. So, it is the arrangement one has to see where the minimum the size means length of the pipeline is adjusted, so that the cost does not go high. At the same time, one has to see that energy used for the making such pipeline arrangement, it is minimum energy is consumed, so that the pump can be also of a smaller size. So, this is one of the arrangement which has been considered in the present design. And so, after the main is brought up to the center, and then sub main pipeline is attached. So, sub main can be laid from the center of the field. So, this is your sub main part, which is connected from the main pipeline, and then it goes to and the up to the 97.25 meter of the length of the field. So, 97 we are not taking up to the end of the field, means we are able to reduce the means 2.75 meter length, because the plant part of the area. So, when we are adjusting considering the spacing between the rows, and then laterals are laid on the both the sides. So, means one lateral you can see on the either side of the sub main pipeline, laterals have been attached. So, when we are making the length, you can see here the main pipeline is of 50 meter, sub main pipeline is of 97.25 meter, and then laterally is of 47.5 meter. That is, so this way we are means making the layout, and then we also because the size of the field is known. So, we know what will be the length of these pipelines. Now, laterals are connected on both the sides of sub main. This is the way one can do and reduce the length, so that the emission uniformity can be maintained. If the length of the pipeline is very large, then with the means when you are delivering the water, so discharge is decreasing with the space. This is a spatially varied flow with decreasing discharge problem. So, at the when the water is being delivered, so there will be more head loss, and then it may happen that the emission uniformity may be reduced, means water is coming out of this your dripper, it may not get adequate pressure at the end. So, it is better to have shorter length of the pipeline. So, up to 100 meter there is as such no problem, but if we reduce the length of the pipeline, we will get better uniformity of water application. So, this way each lateral when we are giving that each lateral will provide water to 10 number of citrus plant. So, this way we are getting the number of plants which can be irrigated with the help of. Now, we will work out what is the discharge through each lateral. So, first of all let us try to know that what is the discharge through each lateral. So, first we will calculate the number of laterals. So, number of lateral is given by 100 meter is the width of the field. Let us see that once again the layout. So, the layout it says that you can see here the 5 meter by 5 means 5 meter is the spacing between the plants, and 5.5 meter is the spacing between the rows. So, this 5.5 meter which has been used, that will decide that how many number of laterals will be coming in 100 meter long field. So, this is coming that 18 number of laterals will be required. So, total number of laterals, because it is on the both the sides. So, in one side it was 18. So, both the sides it will be 2 into 18, that is 36 number of laterals. Now, we found out there will be 10 number of plants on each lateral. So, discharge carried by each lateral is because there are 3 emitters of 4 liter per hour, that is given to each plant. So, there are 10 plants. So, number of discharge carried by each lateral is 10 into 12, that is 120 liter per hour, which is equal to 0.33 liter per second. So, per hour is changed to per second. Now, we will also know that what is the total discharge of 36 laterals. So, total discharge carried out by the 36 lateral is 120 into 36. So, this is coming as 4320 liter per hour, which is equivalent to 1.22 liter per second. So, this way one can get the discharge of 36 lateral. Now, each plant is provided with 3 emitters. So, therefore, number of emitters will be 36 into 10 into 3. So, 1080, this is the another important information which we are getting. So, for 1 hectare area, number of total number of drippers are 1080. Now, we have been given discharge of a pump as 2.5 liter per second. This data will be used to find out how many manifolds, sub main manifold are required. So, if we take the discharge of the pump as a 2.5 liter per second, so which is equal to 9000 liter per hour. So, number of laterals that can be operated by each manifold. So, we have got, if you once again see the previous part, that we have got 120 liter per hour is the discharge carried by each each lateral. So, we will be getting that how many number of laterals that can be operated with the given pump discharge. So, this is given as we are getting 75. So, the pump which has been, which is available with us, is able to meet the requirement of 75 number of laterals. So, means this one manifold is enough, rather more than enough, I will say, that will meet the water supply to all the laterals at a time. Now, having given this data which we have worked out, we will now find out the size of the lateral. So, once the discharge carried by each lateral is known, then the size of lateral can be determined by estimating the head loss due to friction, and this could be estimated by any one of the equations. So, one means it could be by Hagen-Williams equation or by Darcy-Weisbach equation. These two equations are commonly used. So, this head loss due to friction from 100 meter long pipeline using Hagen-Williams equation can be given by this is a unit constant, that is 1.22 into 10 is to power 12 multiplied by discharge of one lateral and divided by C to the power 1.852. So, Q is the discharge, C is the this is a constant that depends on the type of pipe material. The value of C, it changes with the type of pipe material as well as the size of the pipeline, means diameter of the pipeline, and then D is another part, that is the diameter of the pipeline, and F refers to the reduction factor. So, we will be substituting the value and having the appropriate units of these the as it is given in the constant. So, we will use the value. So, first let us work out the reduction factor. Here reduction factor this is due to number of outlets provided in the lateral pipeline. So, number of outlet, we know there are 10 number of plants in each lateral, and in 10 number of plant, for each plant there are 3 drippers. So, number of outlets is this your this is equal to your 30, and then the we have the value of this is as 1 by m plus n plus 1 by 2 n. This is m minus n divided by 6 n square. This m n these are the constants which are used in the Hagen-Williams equation. So, m and n value will be used, and capital N is the number of outlets. So, we are substituting the value of m n and capital N, and then the value of the reduction factor is estimated, and this value is coming as 0.367. Now, head loss due to friction in 100 meter pipeline, we are substituting the value of Q and then C, that is a capital C. So, this is in liter per second, means Q is in liter per second, C capital C is 130, and then the diameter of the pipeline, it is assumed as if we are using 12 millimeter size of the that is the diameter of pipeline, and 0.367 is the reduction factor. So, we are getting the value of head loss due to friction from 100 meter pipeline is 0.54. Now, in actual field situation in our problem, we know that the length of the lateral pipeline is 47.5 meter. So, we will work out for 47.5 meter what will be the equivalent head loss due to friction in the lateral pipeline. So, equivalent head loss due to friction in the lateral pipeline, when we are multiplying with this 47.5 divided by 100 with 0.54, we get the value as 0.26 meter. So, permissible head loss due to friction is 10% of 10 meter, that is the head required to operate the dripper which is delivering 4 liter per hour. So, therefore, 12 millimeter pipeline which has been selected is adequate. So, this is the one part, that is the pipe size of 12 millimeter is adequate to use in the design part. Now, we are coming to the discharge from the sub-main pipeline, and as well as selecting the head loss due to friction for finding out the size of the sub-main pipeline. So, total discharge from a sub-main pipeline is number of laterals multiplied by discharge from a single lateral. So, number of laterals are your there are 36 laterals, and then discharge of each lateral is 120 liter per hour. So, this is coming to 4300 liter per hour, which is equal to 1.2 liter per second. Now, if we assume the diameter of submain pipeline is 50 millimeter, if D, capital D is assumed as 50 millimeter, the values of parameter of the Hazen-Williams equation, because the pipe size it is not the same material, we used capital C as 130 for lateral, which is of LDPE, material was linear low density polyethylene. Here the pipe material could be another, it could be PVC, it can be HDPE. So, value of C is 150. Q is known, that is 1.2 liter per second. Diameter of submain pipeline is assumed as 50 millimeter, and this is the unit constant, that is 1.22 into 10 to the power 12, and F has been calculated by using the same reduction factor formula. So, here we are substituting the value of F, which is coming for the 36 number of your laterals. This is 36 number of laterals. So, n is 36 number of laterals here. So, we will multiply with 2, means we will get the expression for 36 number of lateral as 0.364. So, head loss due to friction from 100 meter submain pipeline, when we are substituting the value, we are getting 0.31 meter or 100 meter pipeline. Now, since this pipeline is of 97.25 meter, so accordingly the value of the head loss due to friction is 0.30 meter, instead of 0.31, now it is 0.30 meter. So, frictional head loss in the submain pipeline is 0.30 meter. So, head required at the inlet of submain pipeline, which will supply water to the lateral pipeline. So, we will know that what is the total head required. So, this is coming as the head required to operate the emitter is 10 meter, head required head HF of lateral, this we have calculated, that is head loss due to friction in the lateral pipeline is 0.26 meter, and the head loss due to friction in submain pipeline is 0.30, and the slope is if you see the field, let me just show you once again the layout. So, slope is in this direction, means from south to north direction, and it is coming up to the 97.25 meter in the length. So, it is almost 0.4 meter in the length. So, this I am which we are getting here. So, what we are seeing here, the slope is 0.4 meter. So, total head loss at the inlet of submain pipeline is 10.96 meter. Now, let us try to know that how much the pressure variation it can have. So, when we are getting the pressure variation, so what we are doing here, we have got 10.96 and then 10.26. So, 10.96 minus 10.26 divided by 10.96. So, if you work out, you will get the pressure head variation is 0. This is 6.38%. So, 6.38% is very less value, which is coming here. So, this is we can see whether can we go for lower size pipeline, so that we can reduce the cost. So, estimated head loss due to friction in the submain pipeline is lesser than the recommended 20% variation. Hence, we are reducing the size of pipeline from 50 millimeter to 35 millimeter. So, for when we take these lower size pipeline means 50 to 35 millimeter, we get head loss due to friction as 1.75 meter. So, HF for 97.25 meter, the is will be 1.70. Now, we will work out when we have reduced the pipe size, what is the value of the head requirement at the inlet of submain. So, initially we were getting 10.26, now it is now 12.36. Let us know that how much is the pressure variation we are getting. So, now we are getting 17% pressure variation, this is also within the permissible limit. So, we can reduce the cost of the submain pipeline if we go for 35 millimeter pipe size. Now, we will work out the size of main pipeline. So, here we are considering the size of main pipeline as a 50 millimeter, and then same we are considering the same Hagen-Williams equation, and because there is only one submain which is receiving water from the main. So, here the except the diameter, rest of the parameter are same. So, we are assuming the diameter as 50 millimeter, rest of the parameter means C because it is the made up of the same plastic material. HDP C is taken as 150 and Q equal to 1.2 liter per second, D is 50 millimeter and K is the unit constant. So, we are substituting and we get the value for 50 millimeter pipeline, it is 0.84 meter when the pipe size is of 100 meter. Now, this is a 50 meter. So, half of this will be the head loss due to friction, that is 0.42 meter. So, pressure head variation lies within the 20% of 12.36. So, we accept this value of the pipeline size, that is the means your 50 meter pipe of 50 millimeter diameter is giving the head loss due to friction of 0.42 meter. So, this is acceptable. Now, we will work out the what should be the horsepower requirement of the pump to supply water in drippers in all the laterals. So, here the assuming the head variation due to uneven field and the losses due to pump fitting as 10% of other losses. So, means this is known as a local losses, that is 10% of all the other values. So, we are substituting the value, the means H emitter, that is head means required to operate the emitter is 10 meter. We have got the HF value of the lateral that we have calculated. We have calculated, we know the slope of the means your field, we know the head loss due to friction in the pipeline. So, all these things are equal to 12.36 meter, and HF from the main field is 0.42 and then 10 meter is the head which is given and 1.28 is the all the losses. So, we get 24.06. Now, horsepower requirement can be calculated by using the expression at the total head dynamic head H, which is here all these components which is explained here, that is the head required at the head required at the inlet of the sub main pipeline is 12.36 plus head loss due to friction in the main pipeline, H static plus H local. So, this is 24.6 in meter, and then discharge in liter per second. So, this value we have the your that is 1.2 liter per second, and then 75 divided by the pump efficiency. So, 1.2, that is the discharge, and 24.06 is the head, divided by 75 into pump efficiency is assumed as 60%. So, we are getting the horsepower requirement is 0.64. So, available size in the market is 1 HP, which is enough to irrigate the whole field. So, 1 horsepower pump is adequate for operating the drip system to irrigate 1 hectare area of citrus crop. In fact, it can meet if there is essential other requirement also. This pump can take care when the requirement of the additional area, because it is giving the pump is of higher size. So, these are the other means in all the design calculation which we have got. We have taken the emitter of 4 liter per hour, and then total number of emitter will be required in the 1080. Length of the lateral, one lateral is 47.5, and then the total number of lateral will be 36. So, one can calculate the what is the total length of the pipeline which will be needed as. So, 36 into 47.5 will give us the total length of the lateral, which is of the 12 millimeter in diameter. So, length of the sub main means the length of the sub main is 97.25 meter, which is of 35 millimeter in dia, and then length of the main pipeline is 50 meter, which is of 50 millimeter in diameter, and then the horsepower requirement of the pump is 1 HP. So, like this similar other problem you can work out by referring these books which are given in these references. And then so, let us summarize this particular lecture. We worked out the design of drip irrigation system by taking one numerical example like this. This is a wide spacing crop, and the similar kind of problem it can be worked out for the close growing horticultural crops like vegetable crop, which is of close growing crops, where the spacing is less. Perhaps it will require more discharge, it will require more number of drippers, it will require more length of the pipeline. So, there you can have the optimization problem, how to get the best layout where horsepower requirement as well as the total energy requirement can be reduced. Now, forthcoming lecture it will be dealt on fertigation lecture we will discuss in the coming class. So, thank you very much.